a vertical force and a lateral reaction force. We can call that VA and HA, and we can have a vertical force here with a roller. Let's call it VG. Okay, so we have those three possibilities of the forces. And I think in this past paper, question 1, 2, and 3, we're basically asking us what is HA, what is VA, and what is VG. Okay, we can see here, question 1, what is the support at the roller? What is the vertical reaction at point A? And then what is the horizontal reaction at point A? Okay, so we have question 1, 2, and 3 simply is us or you in your exam, you have a similar question, would be to basically go about using the three equations we have, quite simply, some forces in the X, that'll give us HA. Some moments about point A, that'll give us VG. This would give us HA, and then some moments about point G, that will give us VA. So we can use those three equations and we can very, very simply get those parameters. Okay, I think we should all be comfortable with this. You would expect something like this in your exam, so you're going to have to be able to apply the equations. Okay, so in this problem here, 1, 2, 3 equations is going to give us a reaction force here, a reaction force here, and then a reaction force over here. Okay, I'll post this paper for you. You guys can go and do it. But that is how you would go about solving this problem. Okay, so that's simply a reaction. So I could give you any structure here, right? In this question paper, I gave them a truss. I could give you a truss, a frame, a beam, and as I've mentioned to you already, all we're looking at here is the external forces applied, the reaction forces, and applying the equations of equilibrium. All right, guys. I doubt there are going to be any questions yet. So that first section was covering reaction forces. Okay. Here we now have force diagrams. In this paper, it only counted 2 marks. You would expect more in your final exam because we didn't really have much of an examination on this. All right. We had a small portion being tested so far, but you're definitely going to expect this to be a bigger section in your exam. But there are 2 questions here, but basically I could ask these questions in a different way. I could give you diagrams, I can ask you to do equations, but obviously because it's multiple choice, and I had a discussion with some of your class mates who came to a consultation last week, basically that in your TUTs and in some of the longer questions you've seen, I've asked students to draw the full diagrams, draw the shear force diagram, draw the axial force diagram, etc. Obviously, in an MCQ examination, I can't ask you to draw things, but what I can ask you is to interpret the results. For example, I might give you 4 bending moment diagrams and ask what is the correct diagram for a certain arrangement of loads. Okay, so then it's more about understanding. I'm not expecting you to go about and solve all of the calculations. You could do that and get to the right answer, but that's not what I'm expecting. I'm expecting you to apply understanding to be able to pick which diagram is correct. Okay, so that's one way I could examine it, by giving you options of diagrams and asking you to pick the correct one. Alternatively, I can give you a diagram and ask you to basically use the information from that diagram to give more information or to elaborate, right, by providing an additional step on a calculation. Or I could give you, like in question 4 here, I could give you a question, give you a beam in this case over here, and say, what is the bending moment at point X? All right, so I could ask this at any point. I could say, what's the bending moment here? What's the bending moment here? But I haven't asked that. I've asked you, what is the bending moment in this beam at this point? All right. Now, in the past, how we've solved these problems is we've used a parameter X, a variable X, to define how this force changes. In a problem like this, we are not concerned about how the force changes across the beam. We are interested in what the force is at this point. Right? So all we have to do now is simply cut the structure at that point and either isolate this part of the structure, which would require us to work out the reaction forces, or to isolate this part of the structure over here. And clearly it's in our interests in this scenario here to isolate the right-hand side. So all we're then going to do, cut the structure, put the internal forces like this. We have an applied force here of 1, an applied force here of 3. So we have these two applied forces. We can now sum the moments about this point over here, and that'll give us n. Right? So clearly, if we do this problem, if we sum the moments about this point, this distance here is 2 meters, right? This force passes through that point. It has no moment arm. So the only force that has a moment arm about this point is 1. So basically the moment, it will be 1 times 2. So our moment here is 1 times 2, which is going to be 2. All right? So that would be the correct answer. Sorry, somebody's mic is on. Let's make sure your mics are turned off. If you're not going to ask a question. All right. So that's how we'd go about solving a problem like this. Okay, so what we really have to do here is we have to just cut the structure where the force has been asked for. Okay. All right, so in all three of these cases over here, we're applying equilibrium here, applying equilibrium here, and then finally applying equilibrium on a cut portion to be able to get the forces over here. All right, so the next question here is a theory question. Okay, so what's been given here is a shear force diagram. We have a beam. The beam is supporting a load, and this load basically is not acting over the entire length of the beam. It's acting over basically a portion, an internal portion of the beam. Okay, so the question is asking, considering the beam with applied load in figure 3, as well as the corresponding shear force diagram, which of the following statements is not correct? All right, the shear force is 0 at midspan. That's clearly correct. Here we can see it. There's midspan. The shear force is 0 at midspan. All right. Maximum bending moment occurs at midspan. Yes. Right. This beam is symmetrical. The loading's in the center. We expect the bending moment diagram to look like this. All right. Maximum bending moment is going to be at the center. And we also know where the shear force is 0, the moment is maximum. Okay. So we know here that in both of these cases, we know in both these cases over here that those two are true. Okay, the bending moment is 0 at the supports. That is correct. This is a pin and this is a roller. So we know that this can't transfer a moment, this can't transfer a moment. So this has to be 0 moment here, 0 moment here. That is correct. The bending moment is constant under the uniform load. No, it's not. The bending moment is curved, parabolic under a uniform load. That is the one that is not true. Okay, so you can expect to see questions like this, where basically you're going to have to look at a diagram and make an assessment, not basically on calculations, but more so on understanding. Okay, so there were several aspects here of understanding in this question, right? One of the aspects is utilizing the shear force diagram directly, and then also knowing how shear force and bending moment relate. Shear force is 0, moment is maximum. One aspect. Also, the bending moment diagram under a uniform load is curved. Okay, so those are the critical aspects of that question. Right, any questions? Okay, let's carry on. Okay, so expect a larger portion of this stuff in your exam. Right, also you're going to expect to see a big portion of your exam covering this section as well. Now remember, with stresses, we've covered basically 4 equations. We've covered 4 equations in stress, and then also we have some extra equations which relate stress and strain. Okay, so when we look at stresses, we want to define stresses generally speaking so we can compare them to a material strength. All right, has the stress in the material exceeded the yield strength or the fracture strength or some characteristic of the material. So we want to be able to transform forces into stresses because we may want to make a comparison or an assessment based on stresses. Now, if you recall from your lectures, and I know you guys are studying for this, we have the three fundamental equations for rectangular section or square section on stresses. It's always true that an axial stress is simply the force divided by the area. So that is the axial stress, the stress along the member. We have the bending stress, which, if you recall, is the bending moment multiplied by this term y over I. This here, y over I, is a geometric parameter of the section. All right, remember this y is the distance from the center to the edge, and this parameter I is the geometric stiffness. Well, how stiff geometrically is the section? Okay, so to convert a bending moment force into a stress, we multiply the force by y over r. To convert an axial force in the member to a stress, we simply divide by the area. Okay, so P over A, axial stress, bending stress, M times y over I. And then the final stress equation is shear stress. We can use the sign tau. Tau is 1.5 multiplied by the shear stress over the shear force, over the area. Okay, so what you see here in converting from a force to a stress, we are basically including a geometric parameter. A geometric parameter is involved in the conversion. For axial stress, cross-sectional area. Shear stress, cross-sectional area. Bending stress, it's this y over r parameter. Okay, so those are the fundamental equations for stress. And in your exam, you're given the equations. I'll just show you here briefly what you might expect. So here, for an example, is a sample formula sheet. Axial stress and strain, bending stress, combined bending stress, the equation for I, degree of determinacy, and the delta for the moment area method, the deflection. Okay, so this is what you would expect to see in your exam, right? A simple formula sheet giving you the required equations. All right, so they're all here. Bending stress, shear stress, axial stress, combined stress. And here we have the relationship between stress and strain, which we'll use now as we go through the next problem. All right, so clearly in this case over here, we have a member under tension, and the force here is being applied at the center of the section. Okay, so for that reason, this is direct tension. So the equation we are going to be using is direct tension. So we simply go in here and we say, all right, what is the axial stress? Axial stress is force over area. Force divided by this times this gives us stress. Okay. The next question is for us to work out the change in length delta L. Okay. So we can now go back and look at the equations. And we can see here that delta L we can get by the original length times the strain. And we can work out the strain by getting the stress divided by Young's modulus. Okay, so we can rearrange the equations. So in this case over here, for example, in solving this problem, we might say that delta L is equal, so rearrange the equation here, E times the original length of the member. All right, E is equal to stress over Young's modulus times L0. This stress we've now worked out. This here is given to us. This is given to us. We have this here from the previous question. We can simply substitute those values into the equation, and we can then work out delta L. Okay. And then the final question of that set on axial was to work out the strain. which we actually used in the previous question. No, actually, this question over here wasn't asked for. So in this one here, we just asked for the stress and delta L. So that's how you go about doing it. Work out the stress, use that stress with this value of E, this value of L0. And again, you want to work in millimeters here. So if you want to work in the correct units, remember this here is newtons per millimeter squared. So you would want to use this force here for the stress, 20 times 1,000 to get it into newtons. And you would want to also take this 3 meters times 1,000 to get it into millimeters. So here you would want to work in millimeters, newtons, because this here is given as that units. Okay. If you use those units, you'll get these answers out in the correct format. Okay. All right, the next question is basically given a member now in which one portion of it has a thinner cross section, or let's say a reduced cross section. So it's the same member over here, but now an inner portion, instead of having 20 times 20 as the cross-sectional area, the area is now 100 square millimeters. Okay, so the question then asks, given the yield strength of the bar of the material is 250 MPa, determine whether the tile will yield under the applied load. So really what we're doing over here is we're just checking, is the stress less than 250 MPa? If the stress is less than this value, the tile will not fail. If the stress is greater than 250 MPa, then the tile will fail under the load. Okay, so really it's just a question here of working out the stress. And clearly, if we pull on this member, it's not going to fail here. It won't fail over here. It'll fail in this region over here. Why? Because we know that stress is directly related to area. So the load here is constant. We pull with this load, which means the load is 20 here, it's 20 here, it's 20 over here. It's 20 throughout this section. So the stress is going to be greatest where the area is smallest. And we know this by inspection, right? We know from our lives, it's obvious to us that it's going to fracture or snap here in the middle. All right. Mathematically, this is occurring. It's because the force is constant. The area here is the least. Therefore, the stress is the greatest. Okay. So in this question, all you're going to do is work out the stress over here and compare that stress to that value. Okay. So here we now have a combined stress question. All right. So we're now basically looking at the scenario where we can think about combining stresses to work out the total stress. So we combine stresses basically when we have an axial force plus a bending force acting in our member. All right. So for example, if we had, let's say, a beam and we cut this beam, and there is an axial force and a bending force in that beam, we could actually work out the total stress in that beam by combining the bending moment and the axial force, because both of these forces result in what's called a normal force, as we discussed in class, right? If we look at this scenario over here, what's happening is we're getting two types of forces or stresses on the structure. We're getting this uniform stress from the axial force plus this linear distribution of bending stress. So if we combine this and this, we then get the total stress, right? The total stress potentially on the member. And we're interested here in the maximum stresses from the combination of those two. But both of these forces, this force here being offset, results in an axial force and a bending force. Those two forces in combination, we can work out what the overall stress is. Okay, so that's what this question here is now assessing. and you will see that this question's been broken up. I mentioned this to you guys multiple times that generally in these MCQ types questions, I'll break the problems up. I might give you some information, and then you have to use that information to solve the problem. All right. In this case over here, what's given is I. I has been given. The area has been given. The moment has been given, and P has been given. So in your final exam, I could ask this in a different way. I could ask you to work out N. I could ask you to work out R, work out A. All right. In this problem over here, or in this past exam, I gave the information here. So what was actually being assessed in this question was an application of the problem. There's also understanding here, because remember, when we apply the equation, the total stress equals minus P over A plus minus my over I. Okay? The minus here corresponds to compression. So in the question, we want the maximum compressive stress. So when we solve this problem, we're only going to get one value out because I've asked for compression, which means that value we want here is going to correspond to stress equals minus P over A minus my over I. Okay, so this plus minus falls away now because I haven't asked what the stress here and here is. I've asked what the stress here is at that point. And we have to know the understanding that I've asked for compression. Compression is negative. I've also asked for the maximum compression. The maximum compression occurs on this part of the structure because the force is on that side of the structure. So in this problem here, we apply this equation to be able to get to the correct value. All right. So, and I believe in this multiple choice, one of those answers over there would also have been minus plus, and that would have been wrong. It needs to be minus minus. Okay. So this is a question assessing both understanding and also the application of the equation. All right, this is a simple question. What is the maximum distance E that the point load can act from the center line of the column for a state of pure compression? Right, this is an understanding problem. We can also solve it with the equation, but we know that this aspect here corresponds to the middle third technique. Right, the middle third technique, which has been known for centuries. All right, that if we keep the force in the middle third of the cross section, that will be pure compression. Now, for this to be the middle third, it means that this must be 1 over 6, and this must be 1 over 6. So that means that the force can't exceed 1/6 of the thickness. Okay, if the force goes outside of 1/6 over here or 1/6 over here, we then have tension. So simply, we just need to work out what 300 over 6 is. Okay, which is 50. Okay. All right, now this is again a theory question which you could solve. So I think I mentioned this to you guys in discussions of the previous tests, past tests, going through past test papers, that many of the questions don't actually require you to put a pen down to work out the question. Not many, but some of the questions are not going to require you to actually do a calculation. We could answer this question by doing a calculation, but we don't have to. All right, we can simply, if we have an understanding of what's going on, we understand what the terms are in the equations, there's no need for us to actually go about and solve this. So here, I mean, I've given the forces, I've given the areas, given E, so you could clearly here work out the stresses in both of these columns and compare them, right? So let's look at what the question's asking. Two short columns are shown in figure 7a and 7b. A 30 kilonewton load acts at a value E of 40 millimeters in both cases from the center of the column. So this is a statement now. The stresses in the two columns are identical because the cross-sectional area is the same. Okay, So that's the statement. Is the statement true or false? All right. So if we just look at the equation, stress equals minus P over A plus minus my over I. All right. So in essence, if for that statement to be true, P over A must be the same for both columns, and my over I must be the same for both columns. All right. Clearly, P over A is the same. The cross section is 200 times 100, and the force P is 30. So yes, in both columns, this first term here is correct. But this is not the same in both columns. The moment is the same, but this parameter y over I is not the same. Right? And we know this because why do we place our beams like this and not like this when we place our beams to span distances? We place our beams like this because that maximizes the stiffness. So clearly a beam supported positioned like this and this will have different stresses, and the difference is coming from this y over I. Okay, so the answer here is false. All right, so here we simply now have some questions to assess. I'm not going to go into too much detail here. I don't want to give away too much. I want you guys to also try and answer these questions yourselves. So we know what the equation is here. We know that we want to work out the shear stress in this beam. We're given the cross-section of the beam. We know that the equation that relates shear force to shear stress is this 1.5 Q over A. So for us to solve this problem, we have to work out A from there. We have to work out Q from here. All right, so I'm not going to tell you how to do that. That's something you can think about and think about where shear forces are maximum in beams. But there's not much involved in terms of working out Q. It's quite simple, but that's for you to figure out. Okay, now what we're given here is we're given the shape of the bending moment diagram, and we are given the reaction forces of the beam, the loads on the beam, and the beam cross-section. And again here, the question is asking for what is the maximum bending stress in the beam. All right, so clearly we've given this diagram. The maximum bending stress is there. That corresponds to that point over there. So the equation for bending stress is my over I. From here, we get y. From here, we get I. Portion of the beam here, we can cut, and we can get m. Okay, so this question here in this exam, I think, carried 2 marks. So there were some questions in this past paper which carry slightly higher marks. This one carried 2 marks because it required a few steps here. It required working out I and A for this section, and it required cutting the beam here, using this reaction force here to get the moment here. The moment here is simply going to be 18.3. What 18.3 times 1 meter, that's the moment over there. This would be 18.3. Use the 18.3 in the equation. So you see, I could have cut this and done the whole solution. If we understand what's going on here, this bending moment must be 18.3. Okay. Just checking if there are any questions in the chat. Okay, nothing. All right, so this question here again, I think carried 2 marks because this question is asking for a bit more. A beam is supported by a pin support and a cable. All right, so here it's supported with a pin and supported by a cable. The cross-sectional area of the cable is 60 square millimeters. Calculate the axial stress in the cable. Okay, so a cable can only carry a tension force. That force must be axial. So the stress in this cable is simply the force in the cable divided by the area. The area is given to us. We now just want the force. The force in this cable, if we simply cut the cable here, draw the arrow on there, and we consider equilibrium of that part of the structure, we now some moments about this point over here, we can work out this force. So equilibrium on that portion, get the force in the cable, put that force into the equation, and we get the stress in the cable. Okay. Okay, I'm not going to spend much time here on the trusses. I think you should have a very good understanding now of trusses. Your section of trusses won't be as large as in the past papers, okay? But there will still be trusses. So you're going to have to go through it. But just back to the point, we have two methods, method of sections and the method of joints. All right, you can decide which one to use. Before you even start to apply these methods, look at the truss and ask yourself, which members do I already see don't carry force? And if we look at this truss right here, this is a zero force member. This force can't cancel out at that joint. There's nothing to balance this force out. This must be zero. Similarly, in this joint over here, this force can't be balanced. This force can't be balanced. Zero force member, zero force member. So these here are redundant members. All right, they're not doing anything in our truss. They're simply sitting there having a good time, unstressed. This one here is providing bracing, right, to our structure. But in essence, it's a zero force member. All right, so if I asked in any of these questions, what is CH? CH is a zero force member. What is the force in EF? Zero force member. What's the force in DE? Zero force member. This member here is not a zero force member. It's going to be equal to that reaction force. This here is also going to be equal. All right, and this is going to be equal to that. All right, so these forces here are not zero. They're going to simply balance with those forces. So these guys aren't zero. They are simply going to balance with reaction forces. Okay, and then if asked for any other forces, we can simply cut the structure or consider method of joints. Okay, but before you even started, it's worthwhile looking at the problem to see which members you know are zero force members. All right, clearly here in this problem, what do we know? Let's look at this member over here. This member is not a zero force member. If there was no force applied here, that's a zero force member. This is a force, a tension force. This must balance with that. This here is clearly 20 kilonewtons tension. Similarly, this joint over here, this force acting down is 20. This force is a compression force of 20. Compression. Similarly, at 20, this must balance. This is a 20 force compression. This force can't balance. There's nothing here to balance with. Zero force member, zero force member. Right, so once we know it's 20, 20, 20, 0, 0, purely by inspection, the only forces we can't solve here by inspection is this force and this force. And due to the symmetry of our problem, we know that this force here and this force must equal this force must equal this force. So there are only two unknown forces here, this force and this force. All of the rest we can see by inspection. And again, you won't have as many questions on trusses. There are a lot more in this past paper, but here, this is a way of asking the question in theory. I'm not going to go through this here. You guys can read through it and see if you understand it yourselves. But basically, like the scenario here, if we know where zero force members are, and we know which part of the truss is in tension and which is in compression, then we can answer these questions very, very easily. All right, what we know is this truss under these forces wants to deflect like this. It means that these bottom chord here, the bottom chord here is a tension chord. This top chord here is a compression chord, right? We know this like with beams. When a beam deflects under load, the cracking starts in the bottom. That is tension. Crushing occurs in the top, compression. Compression, tension in a beam, compression, tension in a truss. A truss is essentially a beam, all right? Tension, compression, these members here are carrying shear forces. All right. The same principle applies. This problem here, this question is generally or really just assessing our understanding of how forces flow in a truss. And this again is extended here to question 24. So I'm not going to go through that in too much detail. You guys can go through trusses. I will post this paper for you. I'm not going to give you guys answers. I've given you enough help here for you guys to go through this question paper and develop your own answers. Okay. All right. So next section here is the final section that we discussed in class. Hang on, I see a question from Vanessa. Go ahead, Vanessa.
Can you hear me?
I can hear you, yes, go ahead.
If you don't mind, can you please go back to question 11?
11, okay.
Yeah.
Yes.
I just want to ask, because I understand that with a beam, the depth plays a role, but this is a column, so does the orientation affect how the load affects the stiffness of the column?
Correct. So in the beam, the depth, so in the beam scenario here, if we had, let's say, a beam that was like this, and we now increase the depth of that beam to like that, then yes, clearly we can see here that by going from this depth of beam to this depth of beam, we're increasing I, we're making the beam more stiff, so we will have stresses. Our stresses are going to be reduced, and our deflections are going to be reduced. So here it's by simply increasing the depth. I've done the same thing here by just changing the orientation of the column. So for the column, for this load being offset here by E, this is now the depth term in our calculation because the bending is happening like this, about this axis over here. So this is the depth term which we use in BD cubed over 12. In this case over here, this load is now offset here, and this now becomes the depth, right? So we can see here that in this arrangement here, here is the axis about which the bending is occurring. That's the depth. Here's the axis at which bending is occurring. This is now the depth. So because this is now the depth, this becomes far more critical. All right. If this load is offset here, the bending becomes a lot more critical. So we can think of it like this is a shallow beam, and this is a deep beam. Okay, so that's how we look
Okay,
at it
that
in a
makes
beam.
sense.
And here, simply because I've changed where the load is applying. All I've changed here really is I've said, okay, instead of the load being over here, the load is now over here. So yeah, so you correct, you 100% are correct in your assessment. All that's changed here is where the load has been applied, but that has a massive influence on the stresses. Okay,
Okay, that makes sense. Thank you.
sure, great. All right, so we have two more sections here we're going to discuss: indeterminate structures, and then we'll just discuss briefly a section on loads, which you'll have again also very likely in your final exam. Okay, so trusses, here we are here, 25. Okay, so this first question here is just applying the equation for the degree of indeterminacy, which is also given to you in the back in the formula sheet. equals 3n plus r minus 3j minus h. Okay, so basically this just tells us by what degree the structure is indeterminate and really by how many extra equations we need to be able to solve this problem. And so all we do here is we have to plug the various parameters in. The joints 1, 2, 3, 4, 5, 6, 7, 8, 9. The joints equals 9. The members 1, 2, 3, 4, 5, 6, 7, 8. And the reaction forces is 2 times 4. We have 2 reactions, 2 reactions, 2 reactions, 2 reactions. There's no hinges. H equals 0. We can put that into the problem and get our answer. Okay, so really here it's just applying the equation. If this value comes out as 0, it just tells us that the structure is not indeterminate. If D equals 0, the structure is determinate, and we can solve that structure using equilibrium. Okay, this question here is one that's checking our understanding of the concept of superposition. We have 3 different beams. This beam plus this beam must equal this beam. All right. So what that means that any force in this beam over here is simply an addition of the force here and the force here. So I could ask you for any parameter here. I could ask you, what's the reaction force in any point in here? All you're going to do, or any internal force, it would be the internal force here plus the internal force here. What's a reaction force here? Simply reaction force here plus reaction force here. And the same is true of deflections. If I give you this problem and I give you a deflection over here, that deflection will simply be the addition of that deflection there plus that deflection over there. Okay, so as we discussed in class, we can break up the loads on a structure to look at each load individually, and we add up all those contributions together, we have to get back to the original situation like this. Okay, so I could ask this question in a number of ways, all right? And it's been asked in a very particular way over here. This, again, is now fundamentally asking about bending, as we discussed earlier on. So I think you can all answer this question right now. We're not going to go through it. Based on our discussion on the column earlier on, I think we all know what the answer here is going to be, right? Stiffer, weaker in terms of geometric stiffness. Okay, so there's a reason why we position beams like this and not like this. We can, you might see beams like this, but there's clearly an understanding that in that arrangement, it might be for space requirements. Maybe there's a clearance requirement or space requirement that we might place a beam like this. But if we had that same cross-section like this, we do get a huge advantage like this in terms of deflection, reduced deflection in the beam. Okay. And here we have a question asking for the displacement in the member. Okay, and this is actually the final thing we discussed in the course in that class, where the deflection in a beam like this, we can use a very, very simple method to work out the displacements or deflections in the beam, right? We can use more complex equations for more complex structures, but here we have a very, very simple structure, a cantilever. We all know if you take your ruler, you apply a force to a cantilever, this cantilever is going to deflect down like this. Okay, take your ruler, it's going to deflect like this. We can use a simple equation we have here to work out any displacement in this problem at any point under C, at any point in this beam. We can work out the displacement by using the equation, the area of the bending moment diagram. So the area of the bending moment diagram multiplied by the distance from the center of that area to the point we want. So if I want the deflection over there, that's my distance. If I want the deflection over there, that's the distance. If I want it over there, that's the distance. Okay, times by this parameter x. That's the parameter x, times by the stiffness, 1 over ER, 1 over the stiffness. Okay, so the area of this diagram multiplied by the distance from its center to the point of interest, the point where we want to know what is delta at any of those points, times 1 over ER. That simple equation over there will give us the displacements in that beam at any point. Okay, so in this problem over here, the area of a triangle is half base times height. Half the base is half of 3, which is 1.5. The height is 150. Okay, so here you're going to have a half times 150 times 3. All right. We also know that the geometric center of a triangle, is 1 over 3 times the length, 2 over 3. This is 1 over 3. This is 2 over 3. Basically, the distance here is 2/3. That's 1/3. This is 1/3. That's 2/3 of that length and of that length. All right. So that's where the centroid, the geometric center of that shape is. So if we know the geometric center, we can then say, okay, what is the distance? Let's say it's asking us here for the deflection at point B. Point B is here. Therefore, we're interested in this distance over here. This total distance is going to be this distance, which is 3 meters, plus 2/3 of that length. 2/3 of 3, right? 2 over 3 times 3, which is 2. Therefore, x is going to equal 3 plus 2, which is 5 meters. Okay, so our deflection here at point B will be the area times 5 meters divided by EI is given. And if we do that, we'll get the displacement. Okay, so you'll see in the formula sheet, yeah, it's given to us. Delta area bending moment diagram times x times 1 over ER, area bending moment diagram, distance from the centroid to the point of interest times 1 over beam stiffness. All right. Standard equation that can be applied here to be able to work it out. I see there's a question. Isadora?
Yes. Can you hear me?
I can hear you. Yes, go ahead.
I just wanted to ask in general, I mean, throughout all the examples, the moment curve is drawn under the line instead of above. And I just wanted to ask why.
So we draw the bending moment diagram on the tension side just by convention. So it doesn't matter. It's by convention. So what we see here is when we have a beam, if I have a beam under a uniform load like this, support here, this bending moment diagram will look like this, drawn on the bottom side, because this beam is going to deflect like this. We have tension on the bottom, compression on top. So that's why there we draw the bending moment on the bottom where we have tension. This is a cantilever acting down. So this cantilever deflects like this. So you will see here we have a convex from the bottom. Here it's convex from the top. So here we have tension on top, compression on the bottom. So that's why this is actually drawn on the top here. All right. So it's just by the convention that we draw the bending moment diagram on the side of the beam where we have tension. Okay.
Thank you.
Sure. Okay. Question 29 is a theory question. This one we don't have to solve. We could go about solving it, all right, and then prove it, but we don't have to. We simply asked, is it true or false? We haven't been asked to prove it. The magnitude of the vertical displacement at point C is the same as that at point B because there is zero bending at both points. It is true that there is zero bending moment here and there is zero bending moment here. Right, that's true. But we see it when it deflects like this, and we know from a simple ruler, right? Take your ruler, put the load in the middle, clamp it in your hand, put it in the middle. it will displace the maximum amount there. Okay, so just by inspection, right, we know that this displacement here will not be as big as this displacement over here. For this statement to be true, the beam would need to deflect. Let me just cancel that. Let me draw it here. For that statement to be true, the deflected shape would need to look like this. Straight line. Okay. Straight line. So a deflected shape down to a straight line. That is not going to happen. All right. Instead, it's going to deform like that. Maximum displacement here. Clearly, this displacement here cannot equal that displacement over there. And we can prove it. If we put in the value of x equals 5 for that displacement and x equals 2 for that displacement, we can see that clearly this displacement over here is going to be 2/5 of that displacement over there. That displacement there would be 2/5 of that displacement, not equal. Okay. All right. We now here have some understanding questions as well on how beams deform. So question 30. A simply supported beam with an overhang is shown in figure 18. All right, we're down here, figure 18. We have, so this beam, a simple support. So we have pin, roller with a cantilevering overhang over there. All right. A simply supported beam with an overhang is shown in figure 18A. The dashed line in figure 18B shows the deflected shape of the beam under load. Which of the following statements is correct? Maximum bending occurs at point A. No, there's no bending at point A. This is a straight line. Right? There's no bending occurring over there. Take your ruler, put your ruler on 2 pencils, push down in the center. This will lift up, but this portion is not going to bend. This is a straight, dead straight line over here. Maximum bending occurs at point B. Incorrect. B, all right, is zero bending here. There's zero bending here and zero bending here. Okay, only bending is going to occur between point B and C. Maximum bending occurs at point C. No, that's a pin. The bending moment is going to look like this in this diagram. Maximum bending occurs at point D. Correct. Maximum bending occurs under point D. That's the correct answer. Okay. So again, this problem could have been solved mathematically. You could have plotted the entire bending moment diagram. You get the force here, you sum forces, get reaction force, cut the structure, draw the diagram, and you would have seen 0, 0, 0 maximum. This is not asking you to do that. This is asking to have a general understanding of what's going on here and to know that maximum bending is occurring over here. All right. And the final section then included in this paper was on loading, which was the first section that we covered this year. And again, in this section, we know that basically we have to be able to work out dead load as one aspect. We have to be able to combine dead and live loads, and we have to combine them using load factors or and load combinations. So we have 2 load combinations, 1.2 dead load plus 1.6 live load, and combination 2, 1.5 dead load. Okay, so this first question here, although it looks complicated, it's quite simple. We simply have to work out the area of this R section. We can do that by breaking the R section up into 3 rectangles, work out the area of those 3 rectangles. Once we have the area, we also have the density of the material, we have gravity, and we can work out what the load per meter is. Okay, not too much tricky in this question. It's just getting the cross-sectional area and multiplying that by the unit weight. Okay, now it gets a bit more challenging in this question where you have to basically distribute loads and work out the loads on the structure. We know from our previous examples that here we have girders and beams in this scenario here. So we can break this up by saying half of this load goes there, half of that load goes there, half goes there. So that's how the load is being carried to the beams. The load on the slab per square meter. Remember, this is the load on the slab. The load on the slab is kilonewtons per square meter. We're going to take 1.2 dead load plus 1.6 live load, or the 1.5 dead load, right? The dead load is simply going to be 24 kilonewtons per cubic meter times the thickness, which is 0.2 meters. So dead load is going to be 0.2 times 24, which is going to equal 4.8 kilonewtons per square meter. The live load is given to us here as 5. So clearly we can see here, there's no point in us solving both of these, right? This live load is bigger than the dead load. It's an impossibility. Mathematically, this can't be critical, all right? This only becomes critical when the dead load is much, much greater than the live load. Okay, so generally speaking, this is the critical load case, unless we have a very, very thick slab supporting a very, very small load. All right, that's not, in most cases, in suspended slabs, in housing, in offices, in factories, generally speaking, your live load, the load applied to the structure, is much greater than the dead load. So this is the equation here, which normally governs. And here it would govern, clearly. All right, so simply it will be 1.2 times that plus 1.6 times that. And we'd pick the value from those available. All right. The next question, I think there's 2 more questions here. Yeah, the last 2. We've gone 1 minute over time. We'll finish shortly. So calculate the load on the interior beam, and the last one is load applied on girder A, B, C, D. Okay, I see a question from Lela. Go ahead.
Sorry, Bradley. I see that there isn't much on, well, I haven't seen anything for arches. Is that not going to be a heavy topic for the exam?
Well, I could ask arches, but generally speaking, arches comes into the section on equilibrium. So, yeah, I mean, I could ask arches, but it would come up then as an alternative, for example, to this first question over here, reaction forces.
All right,
Yeah,
thank you.
So in the past, when I have asked arches, because the arch solution is so much longer than the others, because you have an internal hinge, it requires us to then break the structure up. If I do give you a question on an arch, it would look very similar to this, and generally I would give you one of the reaction forces. So for example, if I gave you an arch problem, I might give you one reaction force, which you can then quickly use to work out the other reaction forces. Okay. So
Right.
I wouldn't ask the full problem, because then it's going to take a very long time. And as we've seen in those problems, that it's very easy to make a mistake, which can carry through to multiple cases. So I can ask arches, but it would need to be asked in a certain way so that it doesn't require you to do too many equations and too many steps. Okay.
Okay, thank you.
But you would see, I think you would see it in the section on reactions if it was going to come up. All right. Yeah, so we're now looking at this question here is asking for a point load. What is the factored point load applied to the girder? So we have this scenario here. We have a column, a column, a column, a column. We have girders spanning between those 2 columns, and we then have beams attached to the girders. All right. So, and basically this beam is applying a point load down onto that girder. this beam here applies a point load down to the girder. So this question here is actually asking us for what the reaction forces are. So this question is solved by isolating a beam. What is the maximum load on the beam? And then working out the reaction forces. That would give us the answer to this problem over here. Whereas this previous question is actually asking us for the load on beam BF, which is this beam over here. Okay, so we would then say that for this beam, this is the area, right? So to convert this from a surface load to a line load on the beam, we have to multiply the surface load by this length. So taking the surface load we worked out in the previous question, multiplied here by 3 meters, because 1.5 and 1.5, 3 meters will give us the load in kilonewtons per meter. We then add the dead load of the beam to that, and that'll give us the load on that beam as a UDL. Okay, so surface load on the beam is quite simple. This load on the internal beam requires us to collapse that surface load to a line load and also add in the beam dead load. So here what you would have is you would have the load on the slab multiplied by 3 meters plus the beam factored by 1.2 times the beam dead load. At 1.2 times this plus the design load already factored on the slab, right, from question 31, times by 3 meters to collapse it down onto a load on the beam. All right. Once you've got this load here is the load that goes into here to work out the reaction forces, which are the loads applied to the girder. Okay. All right, everyone. So that's something you would expect to see in your final exam on Friday. Okay, so everything is examinable. Importantly, you will have trusses, but it won't be as dominant as it was in this past paper. All right, guys, so I'll upload this question paper for you on Alwazi, and then also what I'll do is I'll post this video and then give everyone access. Okay. A question from Kylie, I see.
Yes, afternoon, sir.
Hi.
Can you hear me?
I can hear you, yeah.
I just wanted to ask, so a few of my peers and I are just wondering, like, what the implications are of this paper. Like, is there a minimum required of us for this paper to pass the course for the year?
No, there's no sub-minimum for the exam. So basically it counts to like a normal mark from another assessment. So there's no minimum mark required, but even if you're passing the course and you don't come to the exam and you don't get it deferred, you'll fail the course. So if you don't write the exam, even if you already have a passing grade, you'll fail the course as failed absent. So I think you guys should know this, that if you're absent from an exam, you mark down as failed absent. Okay, so that's the only critical aspect really, is that if you don't write the exam, and let's say you're already on 55 out of 100 for the course, you will still fail the course. Okay, so you must write the exam, or you must apply for a deferred. Allegra, go ahead. Allegra, I can't hear you. Not sure if your mic's off. Allegra, can't hear you. Okay, mic not working. Okay, you can go ahead and type your question if you like. Okay, so the weighting of the final exam, test 1 counts 20%, test 2 counts 20%, your assignment counts 20%, and your final exam counts 40%. So your final exam contributes 40% towards your overall mark. Right. All right, everyone. I don't see any other hands raised. So what I will say is I will say good luck. You can go through the past paper. It will obviously be very, very useful towards your preps. Try and get all the answers. And again, tomorrow, I'm available tomorrow, I think between 11 and 2, if you guys have any final questions, right? So I'll be in my office, room H201. You're welcome to pop by tomorrow if you have any questions, okay? If I don't see you, I'll see you on Friday, and good luck. Almost there. Right, great, everyone. Have a good day.